real briefly because I started. Any change to velocity, speed, and direction is an acceleration. If you are turning, even turning at constant speed, your speed is not speeding up, your speed is not slowing down. If your direction changes, that's still an acceleration called centripetal acceleration. Every vector has a magnitude and a direction. The magnitude is given by the formula v squared divided by r, or equivalently r omega squared. And here, what I want to emphasize now is the direction of the acceleration. If I want to turn right in my car, do I turn my steering wheel right or left? I hope that everyone turns right to turn right. Turn their steering wheel right to turn right, yeah? Duh. Okay, well, the direction of acceleration, if you are pivoting about a point on your right, is to the right, towards the inside of the turn. Does that feel okay? You would not believe how many people get this wrong. If you are going in a circle, the direction of your turn is not away from the center. If you want to bend a straight line trajectory into a turn, I am turning my, in this case, I am turning my rightward motion into outward motion. I am rotating, I'm not rotating, but I am orbiting around a point over here. I am turning from going straight into a curve, and the direction of my change in velocity is always towards the inside of the curve. Here's where I think people get screwed up. I want to redraw this graph, this sketch. This is terrible. Here's where I think people get screwed up. In a car, if you're going straight at constant speed, do the doors slam into you? No, right? Duh. Which direction are you thrown if you hit the gas? Which direction is the force on you if you step on the gas pedal? Google form. Which direction is the force on you if you step on the gas? Forward or back? Google question B. Google question B. If I step on the gas, which direction am I thrown? Which direction is the force on me? Yep, and there's the mistake. Okay, 90% of you agree that the direction of the force is backwards. Let me follow this up by saying, do you accelerate in the same direction as the car, the opposite direction of the car? Which direction is your acceleration? Same direction as the car. If you accelerate in one way and the car accelerates in the other way, you're not in the car for long, right? What does Newton's second law say about the direction of force to get a direction of acceleration? Same. You are not flung backwards when the car accelerates forwards. You are experiencing a forward force. Think about it this way. Do you feel the car pushing against your back, pushing you forward? Do you feel the seatbelt pushing you away from the front of the car? Do you feel the seatbelt pushing you backwards when you step on the gas? You feel a force pushing your back. That is the forward direction. You are not pushed backwards, you are pushed forwards by the car, which is accelerating around you. So if you're moving at constant speed, here's your head, here's your head, here's your head. What happens if we're accelerating? If the car is going faster and faster, it is, here's your seat back, for instance. Here's your seat back. The car would, whoa, the car, if it does not exert a forward force on you, you would be behind the car. The car, to get you there, has to push you forward. And then here's the seat back. The car, to get you there, has to push you forwarder. If you are to accelerate with the car, you need a force in the direction that the car is accelerating. Okay, so follow-up question. Google question C. Imagine you're in a bus, right? And the bus driver steps on the brakes. You're flung forward, right? What force is flinging you forward? Google question C. Again, you're in a bus. Think of being in a bus. The bus is driving forward, and the bus driver steps on the brakes. Do you feel flung forward? What force is pushing you forward towards the front of the bus? Aha, someone sees. Imagine this following scenario. You are standing on a bus. The bus driver hits the brakes. You stumble forward. What force pushed you forward? That is Google Form C. Turn to your neighbor and discuss this for a second. Which object is pushing you forward when the bus driver hits the brakes? You are moving forward. Let's say you're moving to the right, to westward. Standing on the bus, you stumble forward. Why do you move forward? If you're not holding on to the bus rail or whatever, I'm imagining standing, by the way. If you're not holding on to the bus rail, aren't you moved forward as the bus brakes? What pushes you forward? Oh, that's a lot of people. Okay. You're not listening to what I just said. There is no forward force. Consider this. If you wish to stay with the bus, you need a backwards force. Hopefully there's friction. Hopefully there's tension as you grab the dangly strap, right? You need a backwards force in order to slow down with the bus. Nothing pushes you forward. Newton's first law says that unless there's a force, you're going to move at the same speed you were. You are not thrown forward. The bus is slowing down around you. You wouldn't hit the front windshield. The front windshield would hit you. Turn to your neighbor and discuss this point. It's not a force. There is no force. Inertia is not a force. Normal weight, tension, friction, spring are force. It's not a force. You're not accelerating forward. You are not accelerating forward. You are, in the absence of force, moving at constant velocity in the bus. If you don't grab the strap, if there were no friction, if you're on roller skates inside the bus, you're going to keep moving and the bus is slowing down around you so that the front windshield is going to smack into you. You need a backward force. You are holding onto the strap or whatever. There's a tension force backward. There better be friction to push your body backward to keep it with the bus. Okay, so again, Suppose you're in a car that guns it forward. If you move at steady speed, then the car is leaving without you. The car has to exert a forward force on the back from your seat back, in order to keep you with it. The car has to be pushing you forward to accelerate you forward, to move in the forward acceleration of the car. If the bus driver steps on the brakes and slows down around you, you don't feel pushed forward. The bus is slowing down around you. So the bus moves backwards relative to you. You move forward relative to the bus, but it's not because there's a forward force on you. It's because there's a backward force on the bus. And unless you also get a backwards force, you can't stay moving in the same way as the bus. So far, so good? Did you learn something? Is this a surprise? Is this weird? Well, now let's see if you can apply it to a turn. I'm going to turn right. Which side of the car do I run into? Which way am I flung? If I turn right in a car, imagine taking a corner to the right. Which way are you flung? Google question D. Which side of the car do you hit? Or hits you? Okay, just about everybody agrees that when I take a right turn, it is the driver's side door that I feel pressing against me. Tell me this, tell me this, tell me this. If I've got something on my left side pushing me, do I accelerate left or do I accelerate right? If something on my left side pushes my left side, which direction do I accelerate? Right, that's right. Okay, I accelerate right if something on my left pushes me. Which direction is the force of a push to the right from your left side? It's pushing you right. Which direction are you accelerating? You're accelerating to the right. Are you being thrown left by the car as you turn? No, you are being pushed towards the inside of the right turn. If you're turning right, the car pushes you right. Otherwise, you're not going to be moving with the car. What's happening? If you were to stay in a straight line at constant speed, if you were to be unaccelerated as the car turns around you, car is starting, I want a gentler turn. As the car is moving forward and turning around you, what's happening? The car's left side has to push you with it to keep you in place. See, I'm being left behind. I'm being right behind. No, I'm being left behind unless the car pushes me right. So again, if I turn right, what direction am I accelerating? What direction is the car accelerating? What direction is the acceleration? Towards the center of the turn. If I am turning right, I am turning about a point on the right. I am accelerating rightward. All of this is to go back and try to hopefully make this somewhat intuitive. The direction of the acceleration is into the turn. And the big misconception that I think drives so many students to distraction, confusion, missed points, lost ideas, is that we mistake centrifugal force for a real thing. Here is the gospel I preach unto thee. There is no centrifugal force. There is nothing on the merry-go-round pushing you away from the center of the merry-go-round. As you go around in a circle, if you are moving leftward with the merry-go-round, you'd better be holding on to the merry-go-round, feeling pulled to the left by it. The merry-go-round is not pushing you away from the center, the merry-go-round had better darn well be pulling you towards the inside of the circle if you are going to orbit the inside of the circle. Think about going really fast. You're clinging on for dear life as you are swung around and around by the merry-go-round or by the Ferris wheel or whatever. Are you being pulled in towards the center of the circle? Which direction is the tension on your hands? Which direction are you being pulled by the rope? Inward, inward. Ropes pull, they don't push. If I am holding onto a rope tied to the edge of a merry-go-round, or holding onto a fan blade, I am being pulled towards the center. Okay, so that's all very well and good, but if I whirl a can of paint above my head on a rope, which direction is the force? If I whirl a can, hey, take something heavy. Why don't you take off your belt, tie your classmate to it, and whirl them around your head? Which direction is the force there? Google form. Imagine the following. Which direction is the force? If I whirl something in a circle on a string. Woof, 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 woof. I'm a sling thrower in the Middle Ages. Chuck it at the enemy. I'm David fighting Goliath. Which direction is the force? And yet again, it's a trick question. The force on what? I didn't specify. The force that you feel, your hand is pulled outward. The thing causing the circular motion feels pulled outward. What does Newton's third law say about the direction that the thing moving feels? What's the direction of the third law, force pair? If the swinger feels pulled out, the swingee feels pulled in. A bucket of paint whirled around your head or whatever, the direction of the force on the thing that is moving is towards you, towards the center of the circle. If you are imagining centrifugal force, that's not real. There's nothing pushing the can away from you. You pull the can in order for the can, you feel the can pull you out because you are the center. By the third law, you are pulling the can inward. The can is experiencing an inward force, an inward acceleration. I have been singing one song to you in 5 different ways. Please turn to your classmates and sing to them briefly. Tell each other the story that I'm telling you here about relative motion, about objects moving around you, the car accelerating in various directions around you, and which direction the force really is in circular motion. Ready, set, go. J.R. Gillel said on what? Oh, yeah, you saw the trick. Hey, can anyone else think of another example of circular motion, preferably an example that makes you think, well, maybe I am flung outward? Another example of centrifugal force that I can debunk. Yeah. Wait, say that again, discus throwers? Wait, that's the opposite direction that you go, right? How do you spin? Do you discus? Do you know how to discus? Okay. Okay, but talk to me about discus throwing. Okay, so how can we imagine the direction of the acceleration of that? The thing is, I don't have enough experience with discus. I did throw one once in ninth grade. I lie? Um, I don't know. Any other ideas for examples that I know of? Yeah, but like the force of air pressure on somebody being flung around, on Dorothy being flung around in a tornado. Yeah, that is absolutely an applicable thing, but I don't have a gut feeling personally for being inside a tornado to make it, I've tried to make it another intuitive connection. Everybody's been in cars, hopefully. Everyone's been in buses. Yeah. I'm looking for examples that everybody has experienced. Oh, what if it's not a shot? What if it's another person? Here we go. Imagine the following. Imagine the following. You and your loved one are twirling around in a dance, right? And you let go. Which direction are you flung? You're not flung outward. Which direction are you flung? Which direction is the force on you if you are staying together? Are you pushing them away from you? Are you being pushed away or are you pulled towards the center? Are you having to exert an inward force? If you're holding a rope, is the rope being shoved against the person? The rope is got tension on it. That tension is pulling you in towards the center of the circle. And if you are leaning back to be leaning away from the rope, so the rope is pulling you inward. If the rope gets cut, if you release hands from your beloved, yes, you're going to fall backwards, but there's nothing pushing you backwards. You're just off balance. Swing around in a circle with a loved one tonight while standing straight up and down. And well, actually, that's not really going to work. Okay, that's a crap example too. Yeah. Yes, absolutely. Well, that's what I was mentioning before. Uh, uh, what I was mentioning before with a what did I say? Didn't I say merry-go-round? A rotor ride. Ah, yes, those are fun. Let's here. Let me ask y'all. Have you seen? Come on, come on, come on. Next slide. There we go. Have you seen these? Yeah, there's a big hoop with chains that go down. And it turns and are you flung outward? No. What direction does tension act on the person? Along the rope. If the rope is going up and inward, the force on the person is inward, up and inward. Part of that up cancels the down of gravity, but the direction of the force, the direction of the acceleration is inward. Let's do a top-down view of this. Let me give you a little bit of an intuition for a top-down view here. Okay, here is the top. I am going to have imagine the wheel. Here is, actually, I guess, here's the top of the thing, and there's a person clinging to, let's say, the right side. Here's a person at some instant, yeah? And here is my initial position. I'm going to draw where the person is and sketch in the direction that they're going. This also connects with problem 2 on the homework, by the way, at a couple of future instants. Let's simplify the diagram a little bit. I don't actually need to indicate that it's going right. Let's show, I don't want to just talk about initial and final. I want to talk about 3 times. This is time 0, time 1, time 2. Okay, time 0, time 1, time 2. Which direction are they going if they're displacing from here to there? If I go from here to there, what is my direction of displacement? Up and a little left, yeah? I'm going to draw a little arrow to say my displacement is this way, my velocity is this way. Let me actually, I've got a nice diagram. I can leave it nice. The direction of my displacement, let me make it red so it actually shows up. My displacement is this way. You believe me? I'm going to call this the velocity from 0 to 1 is pointing up and a smidge left. Which direction is the velocity from 1 to 2? Up and left. Hmm? I haven't really changed much about the up motion. This upness and this upness are about the same. But looky, this is pointing a smidge left. This is pointing a fair bit left. My initial displacement is mostly up. Later, my displacement is more over. Later still, well, hell, I don't have to just say it, I can draw it. Let's draw the displacement at a third at time t equals 3 seconds. Here's where I am at time t equals 3 seconds. My displacement there is, look, I am going still a bit up, a little less up now, bit up, but I'm going much left. Do you see that my displacement goes from a little left to more more left? My velocity is changing in the leftward direction. I am accelerating inward. My velocity is forward, my acceleration is inward. You don't like that. You guys don't know that notation yet. My acceleration is in this case leftward towards the center of the circle when I pivot about that center. Look at how I'm displacing. First I'm going up, then I'm going up and over. That change is over. How do you feel about this? This screws so many people up. Yeah, that's a thumbs up? Good. Okay, so I claim this is a very real acceleration. When you have centripetal acceleration, Google form, does this speed you up or slow you down? What do you think? Google form F. If we've got this v squared divided by r acceleration, plug in velocity, plug in radius, do you speed up or do you slow down with this? Which direction is the acceleration? I claim that there is this term called centripetal acceleration that exists whenever we move in a circle, and I'm asking, is this a positive speeding up acceleration or a negative slowing down acceleration? I will remind you, by the way, again, I will remind you that you speed up whenever your direction of motion and your direction of acceleration are parallel. If you're moving rightward and accelerating rightward, and you're speeding up. If you're moving rightward and slowing down, your acceleration is leftward. Acceleration and velocity anti-parallel, that's a slowy downy. Is this acceleration parallel or anti-parallel or what to this velocity? Let's just focus on a single instant. We got 50-50, speeding up, slowing down. Wrong. All wrong. This is not speeding up. This velocity and this acceleration are not pointing in the same direction, and they're not pointing in the opposite direction. It is turning. It is changing your direction only, but not your speed. Yeah? Your speed is constant, neither speeding up nor slowing down. When I introduced this, by the way, as I was saying, you can speed up, you could slow down, or you can turn. Turning does not mean that you're speeding up, does not mean that you're slowing down. Turning means that you're turning. So when you are moving X-ward, you are accelerating Y-ward, for instance. When you're moving Y-ward, you're accelerating X-ward. That doesn't speed you up or slow you down. That changes your velocity's direction. Nevertheless, it's a really real acceleration, and F equals ma says it needs a really real force. If you drive your car and turn the wheel, if you ain't got no friction between your butt and the seat, if you ain't got a driver's side door pushing you in towards the center of the circle, if you're turning right anyway, you're going to go flying, baby. You have to have a force to push you in that direction. And the magnitude of that force goes with ma. A is v squared on r. The formula I gave you before, m is your mass. It's a really real force, even though y'all aren't yet used to the idea of a force that is an acceleration that doesn't speed up or slow down. It's just a different direction. Okay, so that's my gospel for centripetal acceleration. I'm going to admit to you, I'm going to point out the existence. Wait, where did I put it? Where did I put it? Where did I put it? Here we go. You can speed up or slow down as well. I can move in a circle and go faster and faster. I can move in a circle and slower. I don't have to move at a constant pace in my circular motion. I call constant velocity, constant speed changing direction. I call that uniform circular motion. But you don't have to have uniform circular motion. You can totally speed up or slow down. If an object speeds up or slows down as it turns, there are two more mathematical terms, tangential and angular acceleration. I am removing these from this curriculum. There are already 7 terms yesterday class and 1 term this class. One idea, big idea this class, having both angular and tangential acceleration as well, 2 different ways of describing the same thing. It's dangerous, so I'm pulling it. You need to know that these things exist. If you hear angular or tangential acceleration, that's a possibility. But if you are moving at constant speed in a circle, they're 0. The value of the speedy uppy, slowy downy kinds of acceleration is 0 if you're moving at constant speed. Easy enough? Great. So that is actually what I have just taught you is, well, actually more than half of the questions on this week's homework and quiz. By the way, there is a quiz this week, for real. Sorry that I missed a couple weeks. About half of the questions involve asking about centripetal acceleration, not tangential and angular. If I ask you about centripetal, tangential, or angular, the answer is it's 0 for uniform motion. But that's not all. There's another thing that y'all aren't familiar with. If I say, how tall is this building in bananas? How could you calculate that? If I say that a banana is 2/3 of a foot, 8 inches. If I say that a banana is 8 inches and this building is, whatever, 1,000 inches, how could you tell me how many bananas high the building is? Divide, right? If I divide 1,000 or whatever, I don't even, 1,000 inches high by banana inches high, I get the number of bananas worth that the building is. Yeah? Sort of kind of what division means. Okay, likewise, in this Homework, some of the canned questions that I got ask you to express things in multiples of g. If you calculate your acceleration is 100 meters per second squared, how many g's is that? Google form! Google question G. How many multiples of 10 meters per second squared is 100? If I tell you that I am moving with an acceleration of 100 meters per second squared, how many g's is that? Roughly. Round, baby. Google form G. Tell me how many g's 100 meters per second squared is. Yo. Sure, absolutely. If I tell you that the way to find banana's worth is to divide by the height of a banana, can you tell me how many g's are at 100 meters per second squared? Roughly. Come on, round it. Let me put this another way. Please think about this. There are too many wrong answers here. To say how many blanks something is to say how many multiples of blank make up that thing. How many multiples of g? How many g's do we have to add together in order to get 100 meters per second squared? It's not less than 1. Okay, take another stab at it. If you got a number less than 1, please reconsider. How many times do we have to add g together? By what factor do you multiply g in order to get to 100? That was good enough. 10 is the answer I was looking for. 100 meters per second squared is 10 factors of 10 meters per second squared. I'm rounding. Question, yeah. 10 point whatever. I don't want to do it. I don't want to carry a calculator. Not when I'm making up examples to fit the needs. Okay, so your for God's sake, your what? Your homework will include questions like this. Do this. Do this. Where's this? Here, do this. Calculate for me a centripetal acceleration measured in factors of g. And give it your best shot. Put it in H. Exercise H. Hold on 1 second. I also encourage you all to try to get a feeling for these things, for each unit that you come up with. You should know that right now, hopefully by now, 600 odd newtons, the number I kept giving for weight, several hundred newtons, is the weight of a person. How much does it hurt if I jump on your foot? Several hundred newtons of force worth. Okay. Likewise, I want to give you a feeling for what an acceleration of 10 g's is. You pull 10 g's in an airplane, you're going to black out, maybe die. You pull 20 g's in an airplane, the airplane is breaking apart, even fighter jets. You pull 2 g's in an airplane, and even a commercial airliner might do that. Your car probably accelerates at a g or maybe 2, depending on your car. Half a g for my car. You get a feeling for what these things feel like, and you can rule out wrong answers. In other words, if you calculate that the sea lion pulls 10,000 g's, you're wrong. Yeah, always. And one more time, let me emphasize here the big words here, please. I'm not just telling you lots of separate facts. Please don't tell me in meters per second squared like half of you are. Let me in units of G. How many times 9.8 is your answer, roughly? Again, I'm going to give you a hint that if you pull 10 G's in an airplane, you're blacking out. 1G, a car can almost certainly do, unless you drive what the sort of junkmobile I drive. 100 G's, there's no living life form, no living life form. No life form is going to be living long if you put it in 100 G's acceleration. Okay, here's how to do the problem. The formula that we got in SI units, we have a new formula, v squared on r, that should be in your notes. If we plug in the numbers given, 3.8 squared divided by 0.31 tells us what? Tells us the acceleration in SI units. You put in meters, you put in seconds, you put in kilograms, you put in newtons, you're gonna get out meters, kilograms, seconds, and newtons. Hey, what is this, by the way? 37-ish? 30 what? 47? 47. You're gonna get out SI units. But what did I ask for? I asked for multiples of G. So if I want to express 47 meters per second squared in multiples of 9.8, you can also say, whoa, is equivalent to 47 divided by 9.8 is, what is that, 5? 5 Gs. Oh, another stupid, so silly. The the force required to accelerate you at 5 Gs is 5 times your normal weight. So if you sit in a car, fighter jet, that is accelerating at 5 Gs, if you're 200 pounds, you're going to feel as if there's a 500-pound person sitting on your chest. 1,000, I can multiply. You're going to feel like there's a 1,000-pound person sitting on your chest, pushing that way. So again, G factor, if you are accelerating at blank G's, it requires a force of m times that G to get you accelerating. Oh my God, it's Newton's second law. You can visualize, you can get some intuition about G factor, multiples of G, by thinking about multiply your mass times that. That gives you the weight that you, the force that is acting on you is like that much weight. Okay. I think that is good. Let's do your homework. Let's do the last question that I didn't see. We actually already covered most of the concepts here, but what I was seeing in the 3 o'clock class is that, again, slope has fallen out of people's ears in one ear, and it's been passed to midterm 2 that hasn't really used slope, and we've got to review that. So I will remind you that slope is your change in vertical coordinate divided by your change in horizontal coordinate. If I have a graph of, you can have negative angles. If I have a graph of angle versus time, let's measure in radians. Let's measure in seconds by default. If I've got a graph of theta versus time, what is the change in my vertical coordinate? Delta what? Delta theta. What is the coordinate? Change in my horizontal coordinate? Delta t, right? What term is slope for this graph? Slope delta theta over delta time. What am I talking about? What is delta theta over delta time? Angular velocity. You can have a negative slope. So in general, slope of theta is angular velocity. The slope of angle versus time is angular velocity. What's the slope of angular velocity versus time? How much does omega change per second? How fast does your spin change? What's that called? It's called not in this class, baby. For our porpoises, and sea lions even, we're going to pretend that spin rates never change, right? Because last year even, people died when we talked about angular and tangential acceleration. Not literally. I haven't yet killed a student. Yet. Let's do an example. Suppose I start with, here, I've got an angular, I've got an angle of theta equals, 2 radians, when time equals 1 second. And then down here, I've got theta equals -1 radian. This, as an example, this might be a angle versus time for a yo-yo. Yo-yo spins first one way, then it slows down. Wait, no. This is uniform. Never mind, this is not a yo-yo. There. No. No, 4. There. So if I start at 2 radians at time 1 second, and then sometime later I'm at -1 radian at 5 seconds, Google form I, we're on I. I. Find omega. I should be precise here. This is a vector now. I'm asking for angular velocity. It can go negative. This is I. Hey, give me units too, by the way. Remember what omega, or can you figure out what omega must be measured in? Don't just tell me a number here. I'm curious to see. Do you remember? Can you figure out the units? Use the formula, Luke. What is rise over run here? This is not G's, by the way. Hint, hint, hint. Look at the y and x axes. We're not talking about acceleration. Okay, I really want to hit another example, so here we go. Here's the answer, negative 0.75. What is rise? As I go from 2 to -1, -1 final minus 2 initial equals -3. I have risen by -3 units. What is my run? If I start at 1 and end at 5, final minus initial equals 4. Run is 4. Rise over run is -3/4, negative 0.75. I only gave you one sig fig. If you said -0.8, that would also be full credit. Now, what are the units of rise? Radians. What are the units of run? Seconds. The units of omega are radians per second. Yeah, it's time. Let's keep going. We need to, if slope is still hard, I strongly encourage you seek a resource because I cannot devote further time than this in this class. Let's talk about what happens if you have a wheel. This is problem 2 on the homework. I'm not giving you the exact answer, but I'm walking you through every damn thing you need to do it. What happens if I give you a wheel? A wheelie big wheel. And I'm going to say that I paint a little dot on the wheel. Let's say I paint a little dot on the top of the wheel, and then I spin the sucker. At time 0, I set this into motion. He's spinning around. I will sketch for you position, velocity in each direction, as well as angle and angular velocity as a function of time. Oh, I need to tell you that I'm going to spin it this way. The problem in question says we're spinning the bicycle upside down. We turn the bicycle upside down and spin the wheel. This is not moving horizontally. I'm sorry, the tire is staying in place, it's just rotating. So the spot that you drew is going to rotate around the center, the coordinate center, but the coordinate center is not itself in motion, okay? What I'm saying is the axes here are stationary. The XY axes are stationary. Hey, what's the initial angle if I'm on the Y axis there? Not 0. That's maps, baby. What is straight up? 90, baby. 90. Oh. How many radians? 1.57. Convert 90 divided by 57.3. There. Theta in radians starts at 90, and I didn't tell you what omega is. If I gave you omega, you could find the slope, whatever, don't care. That's what theta versus time looks like if I spin a wheel starting at positive Y position, where the dot starts at the top of the wheel and rotates around clockwise. What's omega as a function of time look like? Try this yourself. Turn to your neighbor. You have 10 seconds. Omega is the slope of theta. What's omega look like? Correct, Aiden. Good. Hide it. Okay, the correct answer is, well, Aiden got it. Straight line, straight horizontal line to be precise, in the negative, in the fourth quadrant. Why would it be negative? Clockwise is negative rotational direction. What's the slope of this line, up or down? Negative. Question. Okay, let's talk about x, y. If my origin is the middle of the wheel, tell me about the initial y value. Big, small, positive, negative, what? Here's 0, 0. Which What is the initial y coordinate? I don't want a number, I just want big, small, positive, negative, blah, or 0. Positive, right? Y means height above the origin. This is starting as high up as it ever gets. If I were to graph y versus t, the vertical position versus time is it starts 1 radius above the origin. Now let me ask you this. Sometime later, imagine this, we hit the right side of the graph. What's my y now, man? Positive, negative, 0, big, small, what? How up am I when I'm on the x-axis? I'm not. X-axis defines y equals 0. Sometime later, my point, the wheel is rotated such that my little dot of paint is below the origin. What's my y now? Negative. Then I go back to the origin, then I go back to the initial position, cycling around. Right? Now let's talk about the shape of this. It is not this. That's reason why. Tell me about the direction of motion immediately before and after starting. Here is -1, 0, time -1 times 0 times 1 milliseconds or whatever. As we rotate around clockwise, which direction am I going? Which direction am I going? We've got x and y directions now. I'm going rightward, which is the x direction. Am I going up and down? What's my initial y velocity? So the initial slope of my position graph is 0. The line does not diagonal. The line starts out, the vertical position graph starts out horizontal. Now let's talk about a little bit later, sometime in the middle. I'm going, I don't know, this is 11 times 12 milliseconds times 13 milliseconds. Am I going up and down? Look, I go down and right. I go down and right. Is there any down in that motion? Is my height changing? Yeah. Which direction is it changing? Upward or downward? Downward. My slope is negative at some later time. Now, I keep going further. When I am passing through 0 height, am I going up and down? Am I going up and down? Am I going down faster or slower than I was before? Here my height change was this much. Here my height change is this much, yeah? So equidistantly spaced time points are moving further in the y direction. What does that mean about the velocity? It is negativer. What does that mean about the slope of position? It is negativer. And then after that, not parabola, cosine. What's the cosine? It goes up and it goes down, and it goes up and it goes down, and it goes up and it goes down, sinusoidally. Okay, so in this particular case, if I am going around in a circle, starting at the top, rotating around clockwise, I'll just tell you, you got a wiggling vertical position. Tell me how I can get from a position graph to a velocity graph. I suggest that you zoom in on the position graph and tell me what the initial slope is. What is the slope doing here? Does the slope start big, small, positive, negative? This slope is positive? This slope is negative? Positive slopes mean they're going up. Negative slopes mean they're going down. Steep slopes are numbers far from zero. Shallow slopes are slopes close to zero. This is as shallow as it gets, baby. This slope, the vertical velocity, I would call it, starts at zero. Now what happens after time zero? I start out zero, then my slope is a little down, a little downer. Oh, what a downer. What is happening when my slope steepens downward? Velocity goes where? Negative. Velocity goes negative. Okay, what happens here? How big is this slope? Is it bigger or smaller than the slopes before? I get to a very steep negative slope. This is as negative as it gets. What happens then? Is my slope positive or negative here? My slopes are getting less negative. My slopes are increasing towards zero. At this time, the slope is zero. Look at a point. Look at a couple of points right next to each other. The rise and the run are zero there. So at this time, I would say my slope is returned to zero. Then what happens to my slope? It goes positive and reaches a max at that time, then goes down, and so on and so forth. If your position graph is a cosine wave, your velocity graph is also sinusoidal, also wiggly, starting from zero and going down, because the slope here starts from horizontal, which is zero slope, and goes down. The slope increases in the negative direction as it gets steeper, pointing downward, yeah? Dust off thine memories of slope. They're not going away. We're not done with graphs just because we've been talking about force. And we're out of time. But I think that I've covered everything that you need to know. Next week, elasticity and energy time. Remember, there's a quiz for realsies. I mean it. I'll open it Thursday. There is a quiz. I'm getting back on the horse.